So today the final lecture about dynamic programming. Today we talk about dynamic programming on subsets and dynamic programming on profiles. What is it? So last time we kind of talked about dynamic programming on subsets. What does it mean? It means that you have a subset as one of the parameters of your dynamic programming. So you have something like d of x, and this x is actually a subset, not a number, but a subset. And we discussed that if the number of elements is small, so if n is small, then 2 in the power of n is also small. Pretty small, let's say. Like say, if n is about like 20, then they have like millions of possible subsets, and million is quite a good number. So you can make an array of size million, and it will be fine. Today we'll talk more about some problems which you can solve using the same approach. One of the most classical problems is to find the Hamiltonian cycle of minimal weight. It's known as traveling salesman problem. What is the problem? You have some graph. Let's say like this. And this is like the cities, and this is our the vertices are the cities, and edges are the roads between the cities. And for each road, you know, like the distance you need to travel along this road, the length of this road. Let's see, something like 5, 2, 3, 4, 7, 3, 2, 3, 5, 6, 7, 8, 5. And you need to visit all the cities, starting from some city. You have some starting city, let's say this is starting city S. You need to start in city S and visit all other cities in some order, and to minimize the total distance you travel. For example, you can start here and travel, let's say here, then here, then here, and here, then let's say here, and here, and here. Like this. In graph theory, it's called the Hamiltonian path. So it's path which visits all the vertices exactly once. And what we want to do, we want to find this path which minimizes the total distance you travel. So for example, in this path, you have 3 plus 2 plus 2 plus 3, it's 10, 15, 21, 26. So the total length is 26. So this is the classical problem about graphs. You're given some graph and you want to build this shortest path. How to solve it? This problem is also known as to be an NP complete. Again, we will talk about what does it mean exactly in the future lectures. I think I usually talk about this in the last lecture of the second semester, when we just discuss more data structures and more algorithms. We'll discuss what does it mean that the problem isn't complete. And it basically means that we don't know how to solve it efficiently, because we'll talk about it on a second lecture. But if the number of vertices is small, you can use some approach which is not polynomial, but good enough for small values of n. For example, if n is small, you can make an algorithm which works in time 2 in the power of n. It will be small enough. And it is actually faster than just iterating over all possible paths, because if you just check all possible paths which visit all vertices, the number of such paths is about n factorial. And n factorial is much bigger than 2 in the power of n. So there's some gradation of non-efficient algorithms. So there are some efficient algorithms like polynomial algorithms. and some non-polynomial algorithms. But you can distinguish between different kinds of non-optimal algorithms. So 2 in the power of n is much less than n factorial. Well, basically, for n equal to 20, 2 in the power of n is like a million, and 20 factorial is, I'm not sure how much, but it's much bigger than million. So if we manage to have an algorithm which works in this time, it will be much better than if we have algorithm which just iterate over all possible paths. Do we need to return the start point? It actually doesn't matter. There are different variations of this problem. In some variations we should finish in the same point, in the same vertex S. In some variations it doesn't mean you need to return. You can finish in any vertex. Different variations, they all are NP complete, and they actually are pretty the same. You can easily move from one problem to another problem. So if you can solve problem which force you to finish in vertex S, you can easily solve the problem when you don't need to finish in vertex S. You just add one additional vertex, add edges of cost 0 to all vertices, and you need to start in this additional vertex and then iterate all vertices and then go back. So in the end you will have the same problem as here. So it's so these all variations are basically the same. There's different variations is when you need to calculate the number of paths, when you need to check if there is a path which visits all vertices exactly 1, and so on. So there are many different variations of a trivial salesman problem, and they basically all are NP complete. So I will just use this variation because it's kind of more natural, but you can do the same for all variations of trivial and salesman problem. So how do you solve this problem using dynamic programming approach? You do it like this. We will build this path one by one. So imagine you start in vertex S and then have some path. So you have go here, here, here. And this is the graph G. And again, how do you build the solution based on dynamic programming approach? You kind of want to find what is the current state of your dynamic programming. So in some middle of your there's a process of building your solution. So you build your solution just by iterating through this path. And what is the middle state of your dynamic programming? Middle state means that you already built this part of the path and you stand in here. So you're standing in some vertex V. And this is the beginning of your path. What should you remember about the beginning of your path to be able to construct the end of your path? Actually, what you need to know about this path is only the subset of visited vertices. So we'll say we only need to know this subset. We don't need to know the order of the vertices in this subset. We just want to remember that these vertices are visited and these vertices are not visited. Cool. So let's fix this subset. Let's say this subset is X. And now our state is fully described by two variables. First variable is this subset X. This is the subset of vertices which are already visited by the path. And this last vertex. This last vertex is where we're standing now. So we'll say we have D of X and V will be the minimal cost to visit subset X and end in vertex V. It's a definition. And this is not actually. That will be a definition. this is the current state of the dynamic programming. Now you need to make a transition. Yeah. So how to make a transition in dynamic programming? You just want to for your current state to find, there are two possible ways. You either want to find all previous states, or you may want to find all next states. It depends on how do you implement dynamic programming. Let's make the dynamic programming forward. So let's find for our current state all the next states we can go from this current state. What may be the next state of the dynamic programming? If we're standing in vertex V, we may go through some edge VU. So from state XV, we may use this edge VU. So what will be the next state? In the next state, we'll have the set of these vertices will be the same plus vertex U. So we'll have X plus vertex U. And the final vertex will be U. So these are the transitions of your dynamic programming. So each time you iterate all possible edges from vertex V and make a transition from this state to this state and recalculate the current minimum in this state. You should be closest, not exactly, you should be almost. So you need to iterate all possible edges. So you iterate all edges going from vertex V and check all these vertices. And for each vertex, just recalculate the minimum in this state. Yeah, this is basically the method of dynamic programming. How does it work? You iterate, you get to current state, iterate all possible ways to get to the next state, and for all possible states, recalculate the value. Or when you do it backwards, you just have the current state and iterate all previous states. V is the last vertex. Yes. So we have some path. We start in vertex S and finish in vertex V. So this is the all path we constructed, and we want to add one more edge to this path. Yeah. Let's write the code. The code is actually pretty simple. So how do you implement this? You start by doing some base of your dynamic programming. So you need to start some starting state of your dynamic programming. What is the starting state of your dynamic programming? Starting state is when you have vertex S. So you have X is the set of one element. One element is vertex S, right? Let's write the actual code. So we need to make a set of one element. It's just one shifted left to S, and we stand in vertex S. And the cost is 0 because we just started the path. We're standing here. This is the only vertex we visited, so the total cost by now is 0. Short distance, yes. No, mean cost, it's mean distance, let's say. It depends on what you're talking about. So usually all the distance is called the cost of the edges. Now we need to make these transitions. So iterate all possible states, and for each state make these transitions. How to iterate all possible states? It's quite simple. We just iterate for all x's from 0 to 2 power n minus 1, and iterate for all v from 0 to n minus 1. Now we get this state, and we want to iterate for all possible. So we have all possible edges, and for each edge we calculate this transition. Let's iterate for all possible edges VU. Is clear enough? No, I'm using kind of strange coding here, but Here I iterate on all possible edges going from vertex V. Let's like this. Out at V. So out at V is the set of all edges going from vertex V. And here we need to check if this vertex U is outside of set X. How to check if vertex U is outside of X? Maybe like this. Let's say X and 1 U equal to 0. So again, we discussed it last time. Here I check that vertex U is not in the set. Yeah. So U is not in set X. Again, how I do it? I make a set of one element, make intersection of these two sets, and check that this intersection is empty. Right? We discussed last time. So, and now we make this transition. So let's say Y will be the set X plus element U. You can have plus or bitwise, or it doesn't matter because U is not in the set X, so I can have plus here, just to make it more clear. But you can have binary or here instead. And now, so this is Y, and now we move from this state to this state. Again, when we move to the next state, we update the dynamic programming value in this state. So we'll update value in YU to minimum in all value YU and the new value. And the new value will be value here plus this one edge. So it will be value for XV plus this edge, let's say length of VU. Like this. So this is the length of this one edge. So the total length of this path will be all this length plus this edge. That's all, that's the whole code. And now in the end you just check what, in the end you iterate over all final vertices and find the minimal result. So you check in which vertex you end your path and say something like result will be minimum of result and the so we need set of all vertices. It's like 1 shifted down to n minus 1 and vertex E. Right? Looks fine. So we just iterate all possible last vertices of the path, and the state when we visited all the vertices and we finish in this vertex is just, this is the set of all vertices. So it's 2 power of n minus 1. So it's all, in binary representations, there's all ones. And here is the last vertex. And we get the minimum of all possible options. That's all. Again, this is one of the possible problems which can be solved using dynamic programming by the subsets. There are various of such problems. Again, how to know that your problem can be solved using this approach? Basically, what you need to know is that in current state, all what you need to know about the current state is some subset of elements. If this is the only thing you care about, like the subset, not the internal structure of this constructed prefix, but only the subset, which it doesn't matter, then you can encode this subset as a parameter of your dynamic programming, and you will have like 2 to the power of n possible elements in this array. That's all. Cool. Anything else? I think it's good enough. Now, what I want to do next is to talk about a kind of similar approach about dynamic programming, but slightly different. It's called dynamic programming on profiles. Any problem on conforces? You can find millions of problem conforces which uses this approach. I don't have any problem set about this exactly, but I believe you can find a lot of problems like this. You can just Google dynamic programming on subset in task tutorial in contest tutorials, and you will find a lot of problems like this. Yeah. So the next topic I will talk about is the dynamic programming on profiles. It is kind of similar because it's also non-polynomial, so there will be some bit masks and so on, but it's slightly more specific about the structure of the problem. So let's write this. In Russian programming school, I'm not sure how it's happened in all other world of competitive programming, but in Russian competitive programming, it all started with some problem from some ancient Russian Olympiad. I believe it's in some middle 90s. It was about the following problem. You have a rectangle m by m, and you want to fill this rectangle with some small rectangles of size 1 by 2. It was called the parquet problem. Something like this, something like this. Here, something like that, and so on. So I have 6, yes, 6 by something. 1, 2, 3. Yeah, so it is slightly offset. It's actually here, and something here, say something like that. Good enough. And here I have 2 by 2, let's say like this. Okay, not the clearest picture, but good enough. And in that problem, you needed to calculate the number of possible ways to fill the rectangle n by m by rectangles 2 by 1. It was called the parquet problem. Like one of the most classical problems in Russian programming Olympiad school. How it's supposed to solve this problem? Actually, fun fact, later it turns out that it's possible to solve this problem in polynomial time, just using some mathematical approach. So if you just need to calculate the number of ways to fill the rectangle, it's possible using some strange algebra things. So how do you solve this? Let's fill this rectangle column by column. So let's go from left to right. And try to fill columns 1 by 1. So at some point, what is the current state of the process? Current state of the process is when you already filled first, let's say I columns of the rectangle. So you fill columns from 0 to I minus 1. So this left part is already filled with this how do you call them? Tiles? let's call them tiles. So you somehow fill all this left part with some tiles to 2 by 1. Now, what do you need to know about this left part to be able to fill this right part? You need to know which of these tiles are going out of this left part. So there are some tiles which are a little bit go out of this left part. So something like that. And what you want to know is which on which rows we have this tile which is going out of this left part. Yeah, makes sense. Sounds like that. There will be empty spaces too. What do you mean empty spaces? No, so this part is already filled. So all this left part is filled with these tiles. So some tiles do not go out of this line. So here we have something like that. Here we may have something like that. But some tiles stretch out. And we want to somehow remember in which rows we have these tiles which go out of this filled left part. Does make sense? So how do we remember this? Basically, what we need to do for each row, if there is this tile going from this left part on, let's say something like this. So this is basically how this is basically where this work profile came from. So you want to remember this like broken line. So this profile of your dynamic programming. How to encode this profile? Well, exactly like we did with the subsets. So for each row, we will remember like we have 0 if we have no tile, and we have 1 if like this. So this n-bit number will specify in which rows we have this one extra square in this right part. That's all. And now just encode this number as integer p. And we have a dynamic programming. So this is the current state of the dynamic programming. We already filled these first I columns, and the profile is p. So we have dip. P is number of ways to fill first I columns with profile p. That's all. Now, we fixed what is the state of dynamic programming. We need to make transitions. So we need somehow to determine from the current state IP what will be the next state. So how to find the next state of the dynamic programming? Again, you have this current profile. Like here, let's have some 0, 0, 1, 1, 0, 0, 1, 0, 0. So here are all columns from 0 to I minus 1. And we want to move from I to I plus 1. So to move from I to I plus 1, we need to fill all these. Let's mark them. We need to fill all these not filled squares in the column I. Yeah. So when we move from I to I plus 1, we want somehow to fill all these empty squares. How to fill them? Well, there are possible ways. So for example, here you may add like 2 horizontal tiles, and here you may add 1 vertical tile, and here you may add 1 horizontal tile, and so on. So when you fill these empty squares, you will end up with some different profile. Let's have the new profile will be this. So we have this first profile. It was 0 0 1 1 0 0 1 0. This was profile P, and we have some new profile. 1 1 0 0 0 0 0 1. Let's say profile Q. And if we fix the way how we fill all these empty squares, we will move from state IP to state I plus 1 and Q plus 1. No, Q plus 1, Q, just Q. Cool. Now, how to check if it is possible to go from profile P to profile Q? It's actually simple. If you have profile P and profile Q, you have some space between them. So if you fix 2 profiles, you have all this space between them. And all you need to do is to check if it is possible to fill all this space with tiles 2 by 1. If it is possible, then you can go from profile P to profile Q. It's not always possible. For some pairs of profiles, it's not possible to go from one profile to another. But you can write a simple function that checks that it's possible to go from P to Q. Is a profile Russian? I'm not sure. I'm not sure what is the story about this naming. I believe I saw this problem in Russian Olympiad, so maybe it's kind of the origin of this term is Russian, but I'm not sure about this. Maybe it was some different contests when they have the same approach and they use different terms. I know, I just learned these terms when in 90s when we had Russian Olympiad. Maybe it's not the original Russian, but I'm not good in history. How to handle the n case? It's quite simple. We will talk about n case in the. Let's write the code and then we will talk about what is the last case. It will be simple. Let's do it like this. So again, how do you make the dynamic programming program? You start from the first state. What is the first state of your dynamic programming? First state is when you didn't fill anything. So when you start from filling 0 columns, and the profile is simple. When you didn't fill anything, the profile is empty. Yeah, so you don't have any of these squares, so the profile will be all zeros, so it's just 0. So starting state will be like this. And we have one possible way to fill empty space. Yeah. Now you make these transitions. You start again from I to 0 to n minus 1. It's n minus 1. N minus 1. And you iterate all possible profiles from 0 to power n minus 1. And now you make these transitions. To make these transitions, I will write simple code. I'll just iterate all possible q's from 0 to 2 power of n plus minus 1. And then I check if it is possible to go from this state to this state. I'll just use some procedure. If let's say these two profiles are compatible if you can go from one profile to another profile. Compatible. Good enough. So if you can go from this profile to this profile, then you move from this state to this state. So you simply make d I plus 1 q plus equal ip. That's the whole code. Now, in the end, how do you finish the dynamic programming? No, in the end, you fill the whole rectangle. Yeah. So what will be the final state? The final state will be when you fill all the rectangle and you have no these tiles out of the rectangle. So the final state is when you fill everything. So you fill all m columns and you don't have any these tiles which stick out of this rectangle. So the profile will be 0. 0. That's all. Yes, you also calculated some strange states when you have all the columns and some tiles are out of this rectangle, but that's fine. You just don't use these states. You only need this state basically. Yeah. So when I equal to m minus 1, you actually don't need all the states q. You only need state q equal to 0. But it's very minor optimization. Okay, clear enough? Is it clear enough? Now let's talk a little bit about this function which checks this possible go from one state to another state. So how do you check? How do you check that it's possible go from profile P to profile Q? No, there are different ways to do it. You can do it just by iterating over all rows and just putting all the tiles in the place. So there's a unique way to fill the tiles. If it is possible to fill all this empty space with tiles, it is actually a unique way. So you start from top to bottom, see if the space is empty, and if you have 0 here and 1 here, it means that you need to place the horizontal tile here. If you have 0 here and 0 here, it means that you need to place vertical tile here. So you just iterate all rows from top to bottom and just place the tile. There's only one way to do it, if it is possible. It may be not possible. For example, if you have 0 here and 0 here, you need to put this vertical tile, and this space is not empty. If you have to put a vertical tile and this space is not empty, it means that it is impossible to do. But I want to talk about a little bit about some bitwise tricks to do it in constant time, just to make it a little bit more interesting. So let's use some bit magic to calculate this function in constant time. No, why should it depend on I minus 2? No, because each tile is only 2 squares in width, so it's only depends on the previous column. So only the previous column may somehow distract this next column, because all tiles are just have width equal to 2. So if we want to fill this column, we only affect the previous column. Makes sense? So we need only the previous columns. Only column I minus 1. Again, so how to check if two profiles are compatible? Let's see. First, what is impossible state? Impossible state, for example, is when you have in profile P you have 1. means you have something like this. In profile P, you have this profile P, this profile. If here you have 1, and in profile Q, you also have 1. It is impossible state, yes, because if you have 1, it means you have a horizontal tile here, but you can't place horizontal tile because this square is not empty. So let's find if we have situation like this. So let's find if we have some bit in which you have both ones in profile P and in profile Q. Got it? So we want to find the situations like this. We have two profiles, P and Q. These profiles are actually n-bit integers. We have this integer and this integer. And if we have ones in the same position, so we have some 1 here and 1 in the same position here. So then these two profiles are not compatible because we cannot fill this square without filling this square. We need to place horizontal tile here, and it's impossible because this square is occupied. So how to check if two numbers, integer numbers, have the same bit, one in the same position? Any ideas? Let's make it a little bit more interactive. Just say any ideas. That's not that tricky. Again, what I want to check? I want to check that I have this bit equal to 1 in both P and Q. Yeah? If there is at least one such bit, it means that these two profiles are not compatible. Yeah, cool. Why not B? Just B. No. Okay. we have two answers. Actually, you both are quite close, but not exactly. How you do it? You calculate the bitwise end of these two numbers. So calculate this number P and Q. So it's 1 ampersand here because I want to make a bitwise or not end, not the logical end. And it will check if we have this bit in the same position. So if we have it, we have 1 here. So if this number is not equal to 0, it means that we have at least one bit with two ones. Let's check this. So if P and Q are equal to 0, return false. Cool. Now, what else do we need to check? Let's see. So we have. So what else do we left? If we have 1 and 1, it's already false. If we have 0 and 1, so if profile P we have 1, let's see, and in profile Q we have 0. That's always fine, because if we have 1 here and 0 here, it means this square was occupied by some tile, and we just don't do anything. We just in this row we don't put anything because this square is already filled with some previous tile, so we just left it as it is, and we have profile 0 in the next column, right? So this is already so here we have false, and here we have true. What are the situations left? We may have 0 here and 1 here. like here. So we have 0 here and 1 here. What does it mean? It means that we need to place a horizontal tile here. So place a horizontal tile here. It is always possible. If we have bit 0 here and bit 1 here, we can always place this horizontal tile and it's fine. It is the only way to get this bit equal to 1. Yeah. So this combination is always fine. And the final combination is 0 and 0. Yeah. So we have 0 here and 0 here. Like here, we have 0 and 0. It actually means that we need to place vertical tile here. So we have this vertical tile. So we get from state 0 to state 0. Yeah, got it. Yeah. Again, just say something in the chat if everything is clear or if not everything is clear. So, because sometimes my chat is frozen. My chat freezes. Difficult language. We can check two conditions if it will be 0 and then if a is inside. No, the second condition will be a little bit more complicated. So what should we check here? When we place vertical tile, we actually need two consecutive rows to have 0 and 0. So we need to have 0 and 0 here, and also have 0 and 0 here. So all these combinations 0 and 0 should come in pairs. Yeah? You kind of need to split all these 0, 0 pairs in pairs. So here we have 0, 0, and here we have 0, 0. And this is what you need to check. You need to check if all 0, 0 pairs, again, take a common pairs. Why the answer is M? No, it's M0. I start from 0. I start from 0 and end at M. No, it's quite fine. So this is not included. First I columns from 0 to I minus 1, like here. So in the end, I fill all M columns from 0 to M minus 1. No. This part is pretty fine. I'm quite sure about this. Again, it's usually how do you write dynamic programming? You start from 0 and end at N. So you make M iterations from here to here. So you fill all M columns. Now, again, I will go back. What I want to check? I want to check that if I have 0 here and 0 here, then all these bits can be split in some pairs of two consecutive rows. Whew. How can I do this? First, let's beat the following. Let's build the number which contains ones in these positions. So I want to build a number like this. So I want to have 1 in the same positions when I have 0 in P and 0 in Q. How is possible to build this number? No, it's quite simple. I need to have 0 here and 0 here. So I'll make not P and not Q and then end these two. Let's name it X. So let's say X equal to not P or not Q. It may have some extra bits, so I just end it with 1 and minus 1. That's fine. So I have all 0 bits here, all 0 bits here, and then I AND them or them. I need AND them, AND. My bad. Yeah, you should do the opposite. You may do the opposite. You may do OR and then make NOT. That's why what I was thinking about it. So you may instead of this you may write NOT or P or Q. It is the same thing, right? Now you make this bitwise number x, and in this bitwise number x you want to be able to split all ones in pairs. So you have this number x. Sorry, it's here. I don't need this anymore. You have this number x. It has zeros and ones. And I need to check that I may split all these ones in pairs like this. How can I do it? Again, using some arithmetic operations and bitwise operations. Oh, yeah, we're a little bit out of time. Okay, cool. So the easiest way to check this is to make the following: is to divide x by 3, because this 1, 1 is 3 in the binary. Yeah. So if you just have x divided by 3, then each this pair will become just 1. Yeah. So again, this pair is 1, 1 in binary, so it's 3. So if you divide it by 3, you will have 1 here, 1 here, 1 here, 1 here, and so on. For each such pair, you will have 1 bit here. Let's call it y. Again, if x is not divisible by 3, then it's false. Then let's say y x. And the final thing you need to check is to check that in this number y, these ones are not next to each other. So if you have two ones next to each other in number y, it means that in number x you have these two pairs overlapping. You don't want this to have. You don't have two pairs overlap each other. So now you need to check that in number y, in this number, there is no two consecutive ones. How to check if number do not have two consecutive ones? It's easy. You take this number, shift it left by 1, and end with itself. So you check that number y ended with number y shifted left 1. If this is not 0, it means there are two consecutive ones in number y. And if it happens, you just return false. If none of this happens, it means that it's possible to get from profile P to profile Q. That's all the tricks I want to show you. Again, that's kind of complicated, but all operations are quite fast. So you don't have any cycles here, so you don't have any loops here. You just have some bitwise operations, arithmetic operations. Here you have the division. It's not the fastest arithmetic operation, but again, it's all faster than just iterate over all bits with some for loop or something like this. Okay, maybe it will be helpful for you at some point. I'm not sure if it's. There are situations when you need to do some tricks like this to make your program works a little bit faster. But Okay. Now, let's talk about time complexity. What is the time complexity of this program? If you write it exactly like this, then it's quite simple. You have m iterations here, 2 power of n iterations here, 2 power of n iterations here. So total number of iterations of these 3 loops will be m multiplied by 2 power of n, 2 power of n, so it's 4 power. Good. If you do it a little bit more carefully, so if you here iterate not for all possible values of q, but only for compatible values of q. So for each profile p, you generate all the compatible profiles q. So here I make very simple code. I just iterate all profiles and check if it is compatible or not. If you do it more carefully, you can generate all compatible profiles. And iterate only for these profiles. It will be faster. No, let's say, for example, for each bit there is no combination 1 and 1. So there is no more than 3 in power of n combinations pq. It's actually a little bit less because you also don't allow to have combinations like 0, 0. So if all zeros and zeros should come in pairs, this also decreases the number of possible pairs of compatible profiles. So the time complexity is at most m power 3n, but actually less. So it's actually 2 point something in power of n. I'm not sure what is exact. I'm not sure what exactly the constant should be here, but you can think about this. How to think about this? You need to calculate the number of pairs of possible profiles. It's some just recurrent formula. You can write this formula for number of possible pairs of n-bit profiles, and then get the correct asymptotics from this. We may do it as an exercise. Again, you're too quiet. Say something. I'm a little bit nervous when the chat is empty. I think that something's wrong. Now, let's go next. How to make this program even faster? To make this program even faster, and actually now I will make the time complexity better, and also I will make the code more simple, because this part is actually quite complicated. So now we will solve 2 problems. First we'll improve the time complexity, and we will make the program more simple. Let's go. So why time complexity is bad? Again, why the time complexity is bad? Because we have too many transitions. The number of states is pretty small, so the number of states is actually 2 in power of n. Yeah, but the number of transitions is big. So in the final asymptotics, we have not 2 in power of n, but something like 4 in power of n, if not careful. Or if you do it very carefully, you'll have some 2 point something in power of n. So this constant is bigger than 2 because we have many transitions. From each state, we have many transitions. So to improve time complexity, what you need to do is to find another way to make the state of your dynamic programming such that the number of transitions is small. Cool. Why the number of transitions is big? Because on each transition we're actually trying to do a lot of things. So when we transition from I to I+1, we need to fill the whole new column, and there are many ways to fill this new column. Yeah? So the number of possible ways is big, so number of transitions is big, so it works slow. How to avoid this? Let's make very small transitions. Let's try to add only 1 square on each new iteration. So here when we move from I to I+1, we add n new squares to our filled part. Let's try to add squares 1 by 1. Try this. So, what happens if you add squares one by one? Then we go, let's say, from left to right, from top to bottom. And the current state of our dynamic programming is like this. We already filled first I columns from 0 to I minus 1. And also we filled first j squares of the new column. Like this. From 0 to j minus 1. So again, we go from left to right, from top to bottom. Each time we fill one new square of our rectangle. Now, what we need to know about this filling? We need to know which, again, some tiles may stick out of this filled part. So we something like this. So here, here. And here, and so on. So again, for each row, we will remember if there is one extra rectangle filled by this tile, which is stick out of this filled part. So we'll have profile like this: so 1, 1, 0, 0, 0, 0, like this. This will be profile P. That's all. Now, our state of dynamic programming is described by three numbers. The number of columns we already filled, this number I. The number of squares in the next column we already filled, this number J. And this profile P. DP means dynamic programming. No. Well, so we start from the current state is we filled I columns here and j squares here and have profile P. Number of ways to fill first I columns plus j squares with profile P. It looks a little bit more complicated because first we had two-dimensional array, here we have three-dimensional array, but actually it's you'll see. So it looks more complicated, but the transitions will be much simpler. So the whole code will be much simpler. Cool. So how to make transitions? Again, transitions. You need to fill one more square of your rectangle. Let's say this square. You need to fill this one square of your rectangle. If you fill this one square, you move from state ij to state ij plus 1. Okay? So kind of want to move from ij to ij plus 1. And see how the profile changes when we move from one state to another. Let's see. So we have this profile here. And we want to move to this profile. Right? So this is I, this is J. So let's look on this one square. We need to fill this one square. There are two possible cases. This square may be already filled or it is empty. How to check if this square is already filled? So, and we have this profile P. If in the profile P we have 1 in this bit, So if this bit is 1, it means that this square is already filled with some tile. So we have some tile which stick out of this left part and already fill this profile. So if this bit is 1, then we just go to, this will be Q. Let's make it like before. This is the previous profile, this is the new profile. So if in profile P we have 1 in this bit, it means this square is already filled, and we just skip this square and go to the next cell. So we go from state ij to state ij plus 1, and in profile Q we have 0 in this bit. Okay. So again, for profile P we have this profile, so we have this square out of this left part. And when we go to this profile, we don't have this square filled with some previous tile. So here we had 1 and here we have 0. That's right. So if P of j equal to 1, then we move from ij P to ij plus 1 Q, and Q will be the same as P, but in position j it will have 0. A little bit more schematic, but good enough. If this bit is 0, it means that this square is empty. So this square is empty, so we need to put some tile in this square. There are two possible cases. We can put horizontal tile. If we put horizontal tile here, then we'll have 1 in profile Q, right? So if Pj is 0, then we move from ijp to state ij plus 1 Q, and Q will be the same as P, but this bit will be 0. So Q in state in bit G will be 1. Cool. And finally, we can put a vertical tile here. What happens when you place a vertical tile here? First, we need both these squares to be empty. So we need to have 0 here and 0 here in profile P. And what we'll have in profile Q? In profile Q, we will have 0 in this position because we don't have this square. And we'll have 1 in this position because this square is now occupied by this tile. So the second thing is when we have Pj equal to 0 and Pj plus 1 equal to 0, then we need to make transition from ijp again to state ij plus 1 Q, and Q is the same as P, but in position j plus 1 it is 1. Q in position j plus 1 equal to 1. Whew. That's all. That's all the options we have. Well, let's write the program. The program will be very simple. We don't need this bit magic, all these tricks. It will be very simple. Okay, so what is the first state of dynamic programming? We start with the state when we didn't fill anything, when we filled it. So we filled 0 columns, 0 squares in the first column, and the profile is 0. And now we just move from one state to another. So we iterate all possible states for y from 0 to m minus 1, for j from 0 to n minus 1, for all the profiles. And make these transitions. Let's go. So how to check if the bit is 1? Well, again, like we did before, we see if this p and 1j not equal to 0, it means that it's 1. We make this transition. So we'll have q equal this, q must be the same as p, but this bit must be turned to 0, so q will be p minus 1j, and we'll have dij plus 1 q plus equal dijp, like this. That's all. That's the first option. So if this square is not empty, we just move to the next profile and set this bit to 0. Okay. Now here, well, we do basically the same thing else. So if this bit is 0, then make this transition. In this transition, we have profile q the same as p, but with this extra bit. And again. Just the same code. And finally this, so we need to check that two these bits equal to 0. We already checked the bit j, so we need to check that bit j plus 1 equal to 0. We also need to check that j is not the last bit, so let's see if j is less than n minus 1, and we need to check this last bit, p and 1 and j plus 1 equal to 0. Sounds like that. So this is when we need to place this vertical tile. If j is the last row, yeah, then we can place this vertical tile here. So we check that j is not the last and both these squares are empty. Looks fine. So make this transition. Our cases with j is not continuous included. What does mean j is not continuous? Not sure what do you mean here. I have three cases. First case is when this square is not empty. I check it here. So here, this square is not empty, so I just move to the next state and modify my profile. Here, if this square is empty, then I can place the horizontal tile here, or if both squares are empty here, then I can place the vertical tile. DP bit masks, that's what we're talking about. We're talking about bit masks and stuff. Good enough. Now that's not all. That's not all. Here we make transitions from ij to ij plus 1, but we also need to make transitions to I plus 1. We need to somehow move from this column to the next column. And these transitions is pretty simple. So we need transitions from I to I plus 1. How to make transition to the next column? Let's see, we have state this. So this state is I and n. So here j equal to n. And let's look on this state. So this profile is I and n, and this profile is I plus 1 and 0. And it's basically the same profile. Here we have first I columns field, and here we have first I columns plus n squares in the next column. And here we have first I plus 1 columns field. It is the same. So we just move from state I and P to I plus 1, 0. And the profile will be the same, because in these both situations we have the same profile here. So here in both these pictures we need to care about this n squared. So the profile will be the same. So we need to have it somewhere here. Di plus 1, 0. P we have the same as di and P. That's all. And in the end, what we need to have in the end? In the end, we need to have again d m0, 0. This will be the result. So the result will be in the number of ways to fill all m columns with 0 extra here and the profile equal to 0. That's all. That's how you make this technique is called dynamic programming on broken profile, because here I kind of have the profile, but this line is not discrete, but it's broken here. It's called the broken profile. Again, in what situations can you use techniques like this? Basically, it is situations when the structure of your program is somehow layered. When you have different layers, and when you build the next layer of your solution, you only need to know the state of the previous layer of your solution. Something like that. Usually there's these situations when you have something like two-dimensional grid and you need to fill it like layer by layer, and you only care about the previous layer, not all the previous. Again, what situations looks like? You need to do something on two-dimensional grid, and when you fill this next layer, you only need to find the state of the previous. You don't care about what happens here. You only care about the state of the previous layer of your structure. What's this? I'm not sure what's this. This may happen in various different situations. Mostly it happens in two-dimensional cases. You need to when you need to build some two-dimensional structure which optimizes something. Here I calculate number of ways, but it is the same when you need to find the minimum something, maximum something, and so on. You may, for example, you may want to assign some costs to all different positions of these tiles and minimize the total cost of all these tiles, and so on. So you may have some optimization problem which solves in a different way. In the same way. Okay. I believe it's enough for this lesson. Maybe talk about. Well, let's discuss one more problem. I'm a little bit out of time, but let's just discuss a little. I will not write the code. One classical problem which illustrates the same method is the following. You need to build. You have this rectangle n by n, And you want to paint all the squares black or white in such a way that there is no square 2 by 2 which is colored in the same color. So let's say you color like this, and this, and something this, and this, and something like this. So there is no square 2 by 2 which is the whole white, or if it is black. So you want to find the coloring of this n by m rectangle in such a way that there is no situations like this. Again, how to find out that this problem can be solved using dynamic programming on the profiles? You look on your problem and you see that when you fill this rectangle, like column by column from left to right, when you already filled this left part of your rectangle, and you want to fill this one new column of your rectangle, you only need to know the state of the previous column. So the only thing you need to know is to know the state of this column, because this is the only part when you can have some squares 2 by 2. If by filling this new column you get square 2 by 2 painted in the same color, it means that you have one of these parts must be in this new column. Yeah. So the another part must be in the last column of the filled part. So you only need to remember the state of this previous column. And if we just encode this state of the previous column as some profile P, we will have, again, we'll have the following state. We'll have filled first I columns, and the state of the last column is P. So this P only describes the coloring of this last column. Can we do it greedily? No. If you just, it depends on what problem you're talking about. For example, there may be some different situations. For example, let's say some squares already have some colors, and you need to color all other squares. So if for some squares you already know some fixed colors, or you want to calculate the number of colorings, or you need to find some optimal coloring. Let's say for each square we have some different cost to paint it black or to paint it white. So maybe some different situations when you can do it greedily because of different restrictions you have in your problem. Yeah, if you just want to find any good coloring, you can just make a chessboard like coloring, and it will be fine. There's no, in the chessboard you don't have situations like this. Again, this is how you make dynamic program on profiles. You make the following state of your dynamic program. You already fill first I columns of your rectangle, and the state of this last column is encoded in this profile P. And if you want to make it on a broken profile, you do it like this. Yeah. If you want to use broken profile, because it is first, the time complexity is better, and second, the code will be much simpler if you use broken profiles. And so what happens? And you have the current profile like this, and you want to move to the profile like this. So you need to paint one square. And how to check if it is possible to paint this square white or black? You need to know the colors of these three squares. So in your profile, you need to encode the state of these squares. So the current coloring of these states will be encoded in your profile P. And again, your current state is, this is Y, this will be J. So your state will be, again, HIP, where I is the number of columns you filled, j is the number of squares in the next column you filled, and p is the number which encodes the state of these n+1 squares. So when you move to the next state, you need to paint this one square, and you check if you can paint it white or you can paint it black. If these three squares have the same color, like for example, if these three squares are painted white, then you can't paint white this, and similarly with black. That's all. That's how you move from one state to another. And in the end, again, you need to move to the next column. So you move from state like I and n to state I+1, 0. And you have basically the same code. It's little bit different because you need to have n+1 squares here. In previous problem we have n bits. Here you need to have n+1 bits because you need to have this one extra square here to have this like corner. That's all. What's to read about this topic? It's complicated. There is not like there is no books about these topics, I believe. So there are a lot of different posts, I believe, in code forces blogs or stuff like that. So there are some posts about dynamic programming on profiles and on subsets, on bit masks, stuff like that. But it's not common topic for algorithmic books. Again, if you are a competitive programmer, then you mostly need to rely on not on books but on some posts in code forces blogs and stuff like that, because it's much more close to the actual computer competitive programming stuff. Books are more about academic stuff, like more about theory. And if you want to perform good on contests, you mostly should rely on some more competitive stuff. Okay, that's all for today.